Hello, and welcome back to our series on Vertex Operator Algebras. This is episode 8, and we are going to dig deeper into the structure of modules for associative algebras. In particular, we're going to introduce the concept of induced modules, which, in a sense, allow us to relate subalgebras to submodules. Our discussion here is a bit technical, but much of what we will have to say will carry over to other types of algebras as well, with suitable augmentation. Also, a word of caution here. FLM kind of gloss over a lot of details from modules and ring theory that a beginner might need to really understand what's going on, so we're going to try our best to rectify that here, today. Let's get started. Our cast of characters for today's constructions are three. A, an associative algebra, B, a subalgebra of A, and V, a vector space and B module. Our aim is to build an A module out of V. You might recall that A has its own natural self-representation by the action of left multiplication. One thing we might try is to form the product of A with V. Now, we know how to do this with vector spaces, but as modules, this product is unclear. When we studied product modules last time, we discussed it in the context of Lie algebras. Blindly following the same prescription, we'd run into two problems, one minor and one major. The minor problem is A and V are modules over different algebras. But that's an easy thing to fix for now, since B is a subalgebra of A. So instead, let's consider B times V and follow our nose. The Lie algebra prescription for product modules requires the algebra action to act like a derivation. B is associative, so let's consider the action of the identity element 1. 1 acts on the product B times V as 2 times B times V. And that's trouble. Evidently, this prescription is not a B module. The rule for the algebra action is wrong. Now, of course, we could try to force it. We could throw in a factor of 1/2 and check the other defining relations, but you'd run into trouble again. And that trouble is that the defining product of a Lie algebra is an antisymmetric bracket. This is why there's such a special relationship between derivations, which are symmetric, and commutators, which are antisymmetric. It allows terms to cancel. For a generic algebra, this is not so. The answer to this puzzle amounts to choosing an appropriate product. As with rings, we can define a module over an associative algebra as being left or right, depending upon whether the algebra acts on the left or right of vectors in that space. This might seem silly until you think of ordered pairs from different representations. If you take the product of two left-handed modules, the order on which the algebra acts is not clear. Whom should be acted on first? Lie algebras were democratic, but this was allowed by the antisymmetry of the bracket. Why not both at the same time? Because the action is quadratic, not linear. But there is another way. If you paired a left and right representation, there's a very natural place to put the algebra action, right in the middle. The product between modules that supports this kind of algebra or ring action is called a middle linear or balanced product. And by the way, the algebra action, either on the left or the right element, is the same automatically. It's also very clear that it satisfies the two requirements for a module, which you can also check as an exercise. Two comments to close this aside. First, it's important to note that generally you cannot extend tensor products beyond 2. Commutative and Lie algebras are special in that regard. Second, this balanced product is part of a universal construction which can be used to completely characterize the tensor product of modules. This sort of universal mapping property defines the algebraic structure up to canonical isomorphism, and FLM will use them again and again to define these sorts of objects. Because the algebra or ring itself is so vital to the definition of the product of modules, the tensor product in this case is often subscripted by the relevant algebra. As an exercise to make sure that you really understand what's going on here, you can try to construct the tensor product of the complex numbers with themselves, using, in the first case, the balanced product based on the complex numbers, and in the second case, the balanced product based on the real numbers. Back to our problem. We were trying to make a B module out of the space B times V. And we're going to use the balanced product, which depends on the B action, so we're going to call it B times V with that subscript. Just like left multiplication, B can be its own module when restricted to right multiplication. We can take B to be a right module and V, as usual, to be a left one. So consider a vector of the form little b cross little v. Now, b is equal to 1 times b, so b times v is equal to 1 times b on v. Indeed, for any element of the form b times v, we can always take it to be of the form 1 times b on v. And since the space b cross v is made up of sums of these sorts of elements, the product b cross v is a module that's isomorphic to v. We are now in a position to discuss the induced modules of associative algebras. The A module, induced by a B module V, is the tensor product A times V. The tensor multiplication is the balanced product defined in terms of the algebra B. Some clarification is in order here. First, the induced module is a left A module. Second, because the product is defined with respect to the algebra B, any vector of the form A times B times V naturally equals A times B on V. Now, FLM constructs this object differently, using a quotient of vector spaces. As an exercise, you can explain why those constructions are equivalent. And so we're back to our main theme. That is, we must pay attention to how our products, our operations, are defined. Incidentally, this beast is sometimes written as follows. We're going to close our discussion of induced modules by tracing FLM's diagram-chasing logic. Now, there is a natural or canonical inclusion map from V to the induced module, namely 1 times V. This fact allows us to use a bit of category theory to determine the induced module up to isomorphism, as we now demonstrate. Given some other A module, say W, and a B module map from V to W, the induced module has a unique A module map to W, say F sub j, such that this triangle diagram commutes. Put differently, F sub j composed with I equals j. Now this is a strong statement, as it dictates the behavior of elements in the complement, A minus B, given the action of B. And it hinges on the properties of module maps and associative algebras. To make that clear, let's explore a consequence of this uniqueness property of the Fj maps. Following FLM, suppose I' is another A module that satisfies the same universal mapping property. So in particular, we can replace W with I' in our original diagram and find a unique map, say phi, from the induced module to I'. But of course, we could reverse this choice and replace W with the induced module for the defining diagram of I', giving a unique map psi from I' to the induced module. Finally, we can replace W with the induced module. They are both A modules after all, so J becomes I, which suggests that there should be a unique map from the induced module to itself, which of course is the identity map. Here's the reason for all this diagram chasing. The composition of psi with phi affords a different morphism from the induced module to itself. But since the map is supposed to be unique, psi with phi must be the identity. Hence, the induced module is determined up to canonical isomorphism. Whew! You know, folks often say that these kind of proofs are boring, and so that's why they skip them. I think they're right. Anyway, in the vlog, I mentioned how absurdly confusing this line of argumentation is. But as we expand upon it, we find that really, there's just a host of implicit arguments that need to be dealt with. Diagram chasing can be serious, even if it feels silly. So you just need to kind of meditate on these ideas a bit. Or at least I did. And that's our show. Next time, we're going to dig a bit further into these sorts of induced module beasties in the context of algebras generated by groups.